Start with a few further examples relating to motion in a straight line, and specifically we'll be dealing with motion that is having constant acceleration. We have a question here, and as usual we have to first summarize our question diagrammatically so that we're able to have an overview of the question before we begin answering it. So in this question we are having, it goes that a particle is projected away from the origin or with an initial velocity of 0.25 meters per second. So we are having a particle, let's say if this is our origin, it is projected from this point with an initial velocity u of 0.25 meters per second. The particle travels in a straight line and it accelerates at 1.5 meters per second. So meaning its acceleration right there is 1.5 meters per second squared. Find, part A, how far the particle is from O after 3 seconds. So we are required to find, let's say it has been moving from here, after here it moved for first second, second, then the third second. So when the time is 3, what is the distance? They are asking how far is the particle. So what is the distance when the particle is 3 seconds away? So of course here, from our equations of motion or of constant acceleration, those equations we derived earlier, we shall pick one of them that is suitable to help us get the answer, one that is having T, A, U, and is required, and S as well. So from that we will know that we shall pick on this one, S is equal to UT plus a half AT squared. We know that our initial velocity u is 0.25, so it's going to be 0.25 meters per second. Multiply that by the time, so the time taken to, the question wants us to find how far after 3 seconds from time. So it's times 3 plus, that's going to be times a half, times the acceleration, in this case which is 1.5 meters per second squared. Multiply that by time squared, which is 3 squared. We need to find the S. And of course there our value, the distance, when you sum it all that up, it's going to be 7.5 meters. So that's our answer to part A. So part B, they're asking us to find the distance traveled by the particle during the 4th second after projection. So it means that the particle has been moving from here for 4 seconds, but in the 4th second. Now there's a difference if they said find the distance traveled by the particle after 4 seconds, then that is different from saying the distance traveled by the particle during the 4th second. So here they want us to find the particle during the 4th second, not after the 4 seconds. So if we were being, so let's try and withdraw. So we'll try and redraw this. If I may redraw this, this is like this. That's the straight line. It's beginning with an initial velocity of 0.25. That is meters per second. And it is having an acceleration, it's moving with an acceleration 1.5 meters per second. So if it is moving on and on and on up to the 4th second, it means that at right here, the value, the time here is 0. So it moves, that's the 1st second, that's the 2nd second, that's the 3rd second, and that's the 4th second. What I'm trying to say here is simple, that at this point, the time there is 0. Here the time is 1. After 1 second, this is time 2. After 2 seconds, after 3 seconds, that is after 4 seconds. And of course, as it's moving after all these times, when the time is 1, 2, 3, 4, the distance covered is also corresponding. So this is the distance covered after 0 seconds at the beginning. Of course, there's no distance covered. This is the displacement after 1 second, the displacement or the distance after 2 seconds. This is the displacement after 3 seconds, and this is the displacement after 4 seconds. So if we are to find, when they ask us to find how much has been traveled, the distance traveled by the particle during the 4th second, it means that from 0 to 1, this is the distance covered in the 1st second, this is the distance covered in the 2nd second, this is the distance covered in the 3rd second, and this is the distance covered in the 4th second. So it means that for us to find the distance covered during the 4th second, which is running from this point to that point, it means that we can get the whole distance covered from the beginning. We can get the whole distance covered after 4 seconds. Then we get the distance covered after 3 seconds. Then when we subtract the 2, we're able to get the distance covered in the 4th second. If I'm to make that clearer using different colors, it means that we're going to first get the distance covered after 4 seconds. The distance from there after 4 seconds. Then afterwards, I will calculate and get the distance covered after 3 seconds. It stems from the beginning after 3 seconds right there. Then when we get this whole distance, subtract that distance, we're able to get the remaining part. And the remaining part is the distance covered in the 4th second, and that's what we want. So it means for us to be able to get the distance covered in the 4th second, like the question is requiring us to do, the formula is very simple. We shall call that, let's call that distance S. So to get the distance covered, let's call it S prime. So the distance covered in the 4th second is going to be equal to the distance covered after 4 seconds, which is S4, minus the distance covered after 3 seconds, which is S3. So right now we need to find S4. What is S4? Meaning that S4 is going to be equal to UT plus a half AT squared. What is the initial velocity here? For the particle to cover up to the 4th seconds, initial velocity is 0.25. So 0.25 times the time. The time is 4 seconds plus a half times the acceleration, which is 1.5. Multiply that by time squared. The time is still 4. And of course our S4 is going to be, so now we get S3. Now, of course, we were able to get S3 from our previous question. Our previous question was asking us to find how far the particle is from O after 3 seconds. So it means that we already know the distance it traveled after 3 seconds from our previous working, or from part A. And part A of that question, which is this here, when we were calculating for the distance traveled after 3 seconds, we got 7.5 meters. So it means that our value of S3 is 7.5 meters. So it means for us to be able to get our answer right here, we are going to simply subtract that the distance covered in the 4th second, which is S prime, is going to be equal to S4. Now we got our S4 as 13 meters, so it's going to be 13 meters minus our value of S3, which is 7.5. And when we get 13 minus 7.5, we are able to get 5.5. So 5.5 meters simply mean that's the answer. That's the distance traveled by the particle during the 4th second. Had the question asked us to find the distance traveled by the particle after 4 seconds, then it would mean that this would be the answer, because this S4 here means that these 13 meters were covered from the beginning up to the 4th second. A car is being driven along a road at a steady speed of 25 meters per second. So if it is starting from here, it is traveling along a straight road. It is being driven along a straight road at a steady speed of 25 meters per second. So it means that its initial speed is 25 meters per second as it's moving. When the driver suddenly notices that there is a fallen tree blocking the road 65 meters ahead, the driver immediately applies the brakes. So it means as this driver was moving, he notices 65 meters ahead that there is a tree, and then he applies the brake. So it means that from the time he applies the brakes, the distance between him and the tree is 65 meters, because the question says that when the driver suddenly notices that there is a fallen tree blocking the road 65 meters ahead, he immediately applies the brakes. So it means, let's assume, according to our diagram, at this point, this is when the driver notices that there is a certain tree here ahead of the road. So when he notices that there is a tree, he immediately applies the brakes from this point. So when he applies the brakes from this point, it means that the distance remaining from this point to there, this distance remaining is actually 65 meters before he reaches the tree. That's according to the question. So we continue. So the driver immediately applies the brakes, giving the car a constant retardation of 5 meters per second. So meaning, as when he applies the brakes, the retardation, which is the value of A, is 5 meters. Now the retardation means it is negative acceleration. So it means the retardation or the deceleration is simply negative 5 meters per second. That's the constant retardation gives. So they're asking us to find how far in front of the car does the car come to rest. Now, let's take note of this. This question is having two kinds of motion. Okay, it is all straight line motion. But we have straight line motion with constant velocity. Then we have straight line motion with constant acceleration or deceleration. In this case, we are having that the first portion of the journey when this car was moving, it was moving at a constant velocity of 25 meters per second. And from our theory, we know that when the motion is constant, when a vehicle is moving at constant velocity, its acceleration is 0. So it means that when we look at our constant acceleration formula, all the common three formula, our acceleration is 0 when the motion is moving at constant velocity. Then from here, the velocity that was previously constant starts varying until it drops to 0 because he applies the brakes. So when he applies the brakes, now the acceleration ceases to be 0, and now the acceleration it becomes constant. Now the acceleration is now reducing at a rate of at a rate of 5 meters per second. It's reducing, it's retarding. So it means the velocity from this point to that point is no longer constant. So it means that because the acceleration, the velocity between this point and that point is varying, it means that the equations that are going to work in between this portion are the constant acceleration formula or equations which we derived much earlier in the earlier videos. So let's get started with the question. Roman 1. How far in front of the car does the car come to rest? It means that when this guy applied the brakes here and he started coming, in between here, he eventually comes to rest before he hits the tree. So the question is how far in front, right there, it's how far in front of the tree. So it means that when the guy applies his brakes somewhere in between here, he eventually comes to rest in front of the tree. So let's say he applies his brakes up to like a certain point there, and it is at that point that he eventually comes to rest. The question is asking, when he comes to rest, what is this remaining distance? How far in front of the tree does the car come to rest? How far in front of the tree? So it means that we're supposed to find the distance he covered. We know the distance from this point to that point, it's 65 meters. So we need to find the distance from that point when he applies the brakes up to that point when he comes to rest. So we know that while he was moving here, he was moving at an initial speed of 25 meters per second. So it means that even while he was at this point, since he was moving at a constant speed, still at this point, his initial velocity here is going to be 25 meters per second. But then when he starts applying the brakes, his velocity drops from 25 up to a certain point here. His final velocity at that point is 0. So we need to find the distance here covered when his initial speed is that, his final speed is 0, and his retardation is 5 meters per second. So we'll get straight with the working. So to get that distance from here to there, the distance he covered, we shall say v squared is going to be giving us u squared plus 2as. We are interested in getting the value of s. So v squared, which is the final velocity, which is 0, squared is going to be equal to u squared, which is 25 squared plus 2 times acceleration is -5 because it's retarding. -5 times s. S is what we are looking for. Now, of course, when we make s the subject of the formula here, we're able to find our value of s as 62.5 meters. So meaning that the distance covered from here to there is 62.5 meters. The distance he covers until he comes to rest. But the question is asking that how far in front of the tree does the car come to rest? It means we are interested in this remaining distance in front of the tree. How far does he come to rest? So it means that the answer here is going to be 65 meters minus 62.5 to be able to get the distance in front of the tree, for us to be able to answer Roman 1. So it means that it's going to be 65 meters minus 62.5 meters, and definitely our answer is going to be 2.5 meters. So it means that for Roman 1, the distance, how far does he come to rest in front of the tree? The answer is 2.5 meters. Now let's get Roman 2. Roman 2 says that if the driver had not immediately reacted and the brakes were applied 1 second later, with what speed would the car have to hit the tree? So now with what speed will the car have to hit the tree? So again, as he was moving, he notices that the tree is 65 meters ahead. He applies the brakes. When he applies the brakes, he's able to stop somewhere before he hits the tree. Now here the question is telling us that what if he had not applied the brakes immediately? So when he does, and then he delays by just 1 second. The question here implies that when he doesn't do so, he is definitely going to hit the tree. So with what velocity does he hit the tree? So it means that since we know that before he had noticed it 65 meters ahead, so meaning that from this point, if he is to delay just 1 second later, it means there's a certain distance he's supposed to cover. So we need to first find the distance he covers in that 1 second when he delays to apply the brakes, so that we're able to subtract off that distance and we're able to deal with our new diagram. Just for clarity, I'll redraw this diagram. So initially he moves at a constant speed of 25 meters per second. As he's moving at that constant speed, he reaches at that point and he realizes that there is a tree ahead, and the tree at that point was 65 meters ahead. So he starts retarding. The retardation is at negative 5 meters per second. He retards at 5 meters per second, or call it the acceleration is 5 meters per second. But now here, Roman 2, the question is telling us that if the driver had not immediately reacted to the brakes and instead responds or activates the brakes 1 second later, with what speed will he have to hit the tree? So it means that he gets to hit the tree. But he hits the tree because he delays to activate the brake by just 1 second. So the question is, in what distance is he able to travel in that 1 second? Now remember that when he was beginning his journey, he was moving at a constant speed of 25 meters per second. Since he was moving at this constant speed of 25 meters per second, it means the acceleration from this point to that point until he applies the brakes is 0, because at constant velocity the acceleration is 0. So to be able to find that extra distance he covers in that 1 second when he delays to apply the brakes, that distance we shall denote as S is going to be the speed, which is u, times the time. The speed with which is moving is 25 meters per second. Multiply that by the time, which is 1 second. So it means that he moves 25 meters. So it means that right here, he moves an extra distance of 25 meters. So when he moves that extra distance of 25 meters, remember that the speed, the tree was initially, he is able to notice the tree when it was 65 meters ahead. In the second instance, when he delays by 1 second from the point he notices the tree, he delays by 1 second to apply the brake, he moves an extra 25 meters. So the question is, at the new point when he applies the brakes, which is after he has now traveled for those 25 meters, at this new point, how much distance is there does he have to hit the tree? Of course, to get the distance remaining to hit the tree is going to be 65 meters minus 25 to remain with 40. So meaning that from here to here you're having 40 meters remaining for him to hit the tree. And of course, while he is at that point, when he applies the brakes, the initial velocity is still the same. The initial velocity at that point, u, is going to still be 25 meters per second. And the final velocity with which he hits the tree, final v, is what we are looking for. And the acceleration is still going to be negative 5 meters per second. So our task here is to find the final velocity with which he hits the tree. So to get the final velocity v, still we are going to say v squared is going to be equal to u squared plus 2as. That's going to be u squared, which is 25 squared, plus 2 times acceleration, which is negative 5. It's negative, meaning it's retarding, times the distance. The distance is 40 meters to hit the tree, and the velocity with which he hits the tree is 50 meters per second. A motor car starting from rest. Again, we are going to summarize our question in a diagrammatic way. A motor car that is starting from rest and moving with uniform acceleration goes 9.5 meters in the 10th second after starting. So if we are to illustrate that diagrammatically, we have a motor car starting from rest, meaning that its initial velocity is 0, and it is going after 1 second, after 2 seconds, and then it continues into the 9th second, then into the 10th second. So it's telling us that it goes 9.5 meters in the 10th second. So it means that between the 9th, between there and there, this is the 10th, because from this is the first, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth. Then the 10th second, it goes 9.5 meters in the 10th second after starting. Find the acceleration of the car. So they want you to find the acceleration of the car and the distance covered during 5 seconds from start. So after finding the acceleration, they want you to find the distance covered after 5 seconds, s subscript 5. Again, here the technique we are going to use is the fact that we know that it is moving 9.5 meters in the 10th second. So it means we are going to get the expression for the distance covered after 10 seconds minus the distance covered after 9 seconds, so that we are able to equate it to 9.5, and within there we are able to get our value of acceleration A. So it means in this case we are going to get the distance covered after 10 seconds, S10, is going to be equal to UT plus a half AT squared. But we know that U, initial velocity, is 0, so 0 times t is, this whole thing is 0, plus a half, so it's going to be a half times acceleration, which you do not know which you're looking for, times time squared. T is 10, so it is 10 squared. So you'll find that your value of the S10, or the distance covered after 10 seconds, we'll call it the displacement after 10 seconds, is going to be 100 A over 2. So that is S10. So now let's go ahead and find the distance covered after 9 seconds. The expression for S9 is going to be equal to, still again, UT plus a half AT squared. That's going to be initial velocity 0 here is 0, so it's 0 times t, this whole term would die, plus a half, so we have a half, times the acceleration. The acceleration in this case, it's going to be not known yet, times the time squared, which is 9 squared, which is 81. So we shall end up with 81A, divide all that by 2. That is S9. So we know that to get the distance covered after 10 seconds minus the distance covered after 9 seconds, we will be able to get the 9.5 meters. Or to make it more clearer for some of us who may not have gotten it yet, we have gotten the expression for how much have we moved after 10 seconds. We've moved from here, that's S10. Then the distance covered after 9 seconds is that. from here up to there. This is S9, like that. So to be able to get the 9.5 means we are going to get the distance covered after 10 seconds minus the distance covered after 9 seconds to be able to get the 9.5. So it means, in simple terms, this simply means that S10 minus S9 is equal to 9.5, and from that expression we are able to get our value of acceleration. So S10 is 100A over 2 minus S9, which is 81A over 2, giving us 9.5. Of course, when we work it out, we shall end up with our acceleration being 1. So that's the acceleration we get. So the other part of the question is asking us to find the distance covered during 5 seconds from start. The distance covered during the 5 seconds from start. It is different from saying the distance covered during the 5th second. Here they want the distance covered during 5 seconds from start. So it means to get the distance covered 5 seconds from start, we shall say the distance covered during 5 seconds from start is going to be equal to ut still plus a half at squared. This is going to be initial velocity, which is still 0, times t, so this whole term is 0, plus a half, which is a half, times the acceleration. We got the acceleration as 1 meters per second, times time, which is 5 seconds, which is 5 squared. So we shall end up with 25. Summarize it diagrammatically. A particle travels in a straight line with uniform acceleration. So the catchword there is uniform acceleration. So meaning you know that you're going to apply the uniform acceleration formula. He's traveling in a straight line with uniform acceleration. The particle passes through points A. So let's call this point A, point B, and then point C. In that order, at time t is equal to 0, 2, and 5 respectively. So at time is equal to t is equal to 0, t is equal to 2, and t when t is 5. So when the time is 0, when the time is 2 seconds, and the time is 5 seconds respectively. So if BC is 30 meters, from here to here it's 30 meters. If BC is 30 meters and the speed at B is 7 meters per second, so the speed at B, let's call it final velocity V is 7 meters per second. Find the acceleration of the particle and its speed when at A. So they want you to find the initial velocity here, and also that is the speed at A. Of course, the speed at A is the initial velocity. So they want you to find the initial velocity, and also they want you to find the acceleration of the particle. So they also want you to find the acceleration of the particle. Now, already in some part of our information, we've been told that between B and C, the object covers 30 meters. So we can use this to find our value of A, the acceleration. We know that we are going to get the expression for distance from A to C. Subtract the expression for distance from A to B, because SC minus SB gives us 30 meters. So let's look at the distance covered at C. We shall call it the distance covered at C. SC is going to be given by, of course we shall be using UT plus a half AT squared. We know that the distance covered after traveling up to C, initial velocity here, we do not know this, so we shall call it U times the time times value of t at C is 5, so U times 5 plus a half times the acceleration, which we do not know because we don't know it, times t squared times 5 squared. Of course, here we are going to end up with 5u plus a half times, this is 5 squared, is going to be 25a. So a half times 25a, so this is like 25a, divide that by 2. So this is distance covered after reaching point C. So let's also get the distance covered at B. SB, distance covered at B, is going to be equal to still UT plus a half AT squared. The initial velocity, of course, it's not known. It's going to be U times T. The T at B is 2, so it's 2, U times 2 plus a half times the acceleration, which we still do not know, times time squared. The time is 2. At the point B, time is 2. So it means that it's 2 squared. And so we shall end up with our SB as 2U plus 2A. So we have our expression for SB. We have our expression for SC. And we know that SC minus SB is giving us 30 meters. So we shall say that the distance covered after C minus the distance covered after B gives us 30 meters. So SC is going to be 5U plus 25 over 2 is 12.5A minus SB, which is 2U plus 2A, is going to give us 30 meters. And so we are going to get an expression in U and A. So this becomes 5U minus 2U is 3U. We have 3U plus 10.5A is equal to 30 meters. So it means that we need to look for another equation from our information that is going to help us to get the values of A and G so that we solve the two simultaneously. Looking at our question, the other information that we can take advantage of that can help us get the second equation is that we have this distance AB, and in this distance AB we are having the initial velocity not given, and then we have the final velocity here, 7. So if we use the first equation of motion, V is equal to U plus AT, we know that our final velocity is 7, our initial velocity is not known, which we are supposed to be getting, and also our acceleration is not known, we are also supposed to be getting it. This simply means that we'll be getting a second equation that is having these two unknowns, and we shall be able to solve those two equations simultaneously so that we are able to get the value of A, which is the acceleration, and also the value of U, which is the initial velocity or the velocity at point A. So we'll go ahead and find that second equation. So getting ours, we know that V is going to be equal to U plus AT. And we know that our final velocity, if you are to consider motion from A to B only, it means if the particles traveling from A to B, B would be the final velocity, which is 7, is going to be equal to the initial velocity, U, which is the velocity at A, which we do not know, plus the acceleration, which we do not know, times A, and then multiply that by the time it takes to move from A to B. The time is 2 seconds, which is times 2. So we end up with 7 being equal to U plus 2A. So we have our second equation. Our first equation was this one. So it means that from these two equations, we solve them simultaneously and get the value of A. Of course, we make U the subject of the formula here, and we substitute the U into there. So if we make U the subject of the formula here, you'll find that U will be equal to 7 minus 2A. So we substitute for this value of U and put it right here. And when we put it right there, we're able to get the value of U and then finally the value of A. So right here, if we are to put it in there, it will become 3 times U. Now the value of U is this one here. So 3 times U, which is 7 minus 2A plus 10.5A is going to be equal to 30. So definitely this is 21 minus 6A plus 10.5A, giving us 30. Negative 6 plus 10.5A is going to give us 4.5A. Is going to give us 30 minus 21, giving us 9. Then our value of A definitely there is 2 meters per second squared. So after getting our value of A as 2 meters per second squared, we can go ahead and substitute for the value of A here so that we're able to get U. So when we substitute our value of A there to get the value of U, we shall end up getting our value of U being equal to 7 minus 2A. 7 minus 2A, A is 2, so 2 times 2, giving us 7 minus 4, and we have our value of U as 3 meters per second. So in so doing, we are able to we will have finished solving the whole question. The question is asking us to find the acceleration of the particle and its speed when at A. So we're able to find the acceleration of the particle, which was 2 meters per second squared, and its speed at A, which so happens to be the value of U, the initial speed, which was U, which we got at 3 meters per second.
This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.